Creep and stress rupture damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of creep and stress rupture based on API 571. The first is at high temperatures, metal components can slowly and continuously deform under load below the yield stress. This time-dependent deformation of stressed components is known as creep. The second is deformation leads to damage that may eventually lead to a rupture. Creep and stress rupture damage are a type of high-temperature degradation. Creep and stress rupture damage refer to a type of material degradation that occurs under high temperature and constant stress conditions. This type of damage is a significant concern in various industries, including power generation, aerospace, and chemical processing, where equipment and components are exposed to elevated temperatures and mechanical stresses. Creep damage. Creep damage refers to the slow, time-dependent deformation of materials under sustained load or stress at elevated temperatures. It is particularly significant in metals, polymers, and other materials that are subjected to high temperatures for extended periods. The process occurs when a material is exposed to a constant load and experiences gradual deformation over time, typically at temperatures above 30% of its melting point. Creep damage is a gradual deformation process that occurs in materials under constant stress and high temperature. When a material is subjected to a constant load at elevated temperatures, the material's atomic structure begins to change, leading to a gradual increase in deformation over time. This deformation can cause the material to elongate, thin, or change shape, which can ultimately lead to a loss of structural integrity. Creep damage is often characterized by: Number 1 is strain accumulation. The material's deformation increases over time, leading to a gradual change in shape or dimensions. Number 2 is grain boundary cavitation. The formation of small voids or cavities along grain boundaries, which can coalesce and lead to cracking. Number 3 is dislocation movement. The movement of dislocations within the material's crystal structure, which can cause plastic deformation and strain accumulation. Creep damage often manifests as necking, elongation, or permanent deformation. In the worst case, it can lead to catastrophic failure if not monitored and managed effectively in applications like gas turbines, nuclear reactors, and high-temperature piping systems. Stress rupture damage. Stress rupture damage describes the failure of a material due to the combination of sustained load and high temperature over a specific period. It occurs when a material, subjected to an applied stress at elevated temperatures, eventually reaches a point where it can no longer sustain the load and fractures. This phenomenon is particularly significant in high-performance materials used in aerospace, power generation, and chemical processing applications. Stress rupture damage is a type of failure that occurs when a material is subjected to a constant stress and high temperature, resulting in a sudden and catastrophic failure. This type of failure is often preceded by creep damage, where the material has undergone significant deformation and strain accumulation. Stress rupture damage is characterized by: Number 1 is sudden failure. A rapid and unexpected failure of the material, often without warning. Number 2 is ductile or brittle fracture. The material may exhibit either ductile or brittle fracture behavior, depending on the temperature, stress, and material properties. Number 3 is cracking and fracture. The material may exhibit cracking or fracture, often along grain boundaries or at locations of high stress concentration. By understanding the mechanisms and factors influencing creep and stress rupture damage, industries can take proactive steps to mitigate and prevent this type of damage, ensuring the safe and reliable operation of equipment and components. Creep and stress rupture damage mechanisms affected materials based on API 571. All metals and alloys. Creep and stress rupture are damage mechanisms that primarily affect materials subjected to high temperatures and sustained mechanical stresses over extended periods. These mechanisms are particularly important in applications such as power generation, aerospace, and petrochemical processing. The types of materials affected by creep and stress rupture include Number 1 is metals. Many high-temperature alloys, including. The first of metals with high-temperature alloys is nickel-based superalloys. Commonly used in turbine components due to their excellent creep resistance, such as NICR, Inconel 600, 625, 718, and 725. The second of metals with high-temperature alloys is cobalt-based alloys. Known for high-temperature strength and oxidation resistance. The third of metals with high-temperature alloys is stainless steel's alloys. Certain grades, especially those with higher chromium and nickel content, are often used in high-temperature applications. Austenitic stainless steels, such as 304L, 316, 321, and precipitation-hardened stainless steels, such as 13-8, 17-4. The fourth of metals with high-temperature alloys is titanium alloys, used in aerospace applications, though they exhibit creep at elevated temperatures, such as T6L 4V, T5L 2.5 SN, and T6242. Number 2 is ceramics. Some advanced ceramics can exhibit creep under high temperature and load conditions. Such materials may include certain oxide ceramics. Number 3 is polymer composites. Certain high-performance polymers and their composites can also exhibit creep behavior, particularly at elevated temperatures. Number 4 is superalloys. These materials are designed to withstand extreme environments, particularly in gas turbine engines and jet engines, where both creep and stress rupture are critical failure modes. Number 5 is refractory materials. Used in furnace linings and kiln components, these materials can be susceptible to creep under high heat and load conditions. In general, materials with a face-centered cubic, FCC, crystal structure tend to have better creep resistance compared to those with body-centered cubic, BCC, structures. The specific composition and microstructure of the materials play a critical role in their susceptibility to these damage mechanisms. Understanding the limits of these materials under specific conditions is essential for designing components that can withstand long-term service without failure. Creep and stress rupture are important damage mechanisms that can affect the performance and lifespan of materials, especially metals and polymers, subjected to high temperatures and loads over extended periods. Here are the critical factors of creep damage associated with each mechanism. Number 1 is temperature. Creep is significantly influenced by temperature. Elevated temperatures increase atomic mobility, leading to the gradual deformation of materials under sustained load. Number 2 is stress level. The applied stress relative to the material's yield strength is crucial. Creep strains are more pronounced at higher stress levels, with the relationship often characterized by time-dependent behavior. Number 3 is material properties. Microstructure, grain size, phase distribution, and defect density significantly influences creep resistance. For example, fine-grained materials may exhibit improved creep resistance compared to coarse-grained equivalents. Number 4 is time. Creep is a time-dependent process. The longer a material is subjected to stress at elevated temperature, the more significant the deformation, creep strain, becomes. Number 5 is environment. Chemical environment, such as oxidation, carburization, can impact creep by affecting the microstructure or causing premature failure mechanisms. Corrosive environments can exacerbate creep damage. Number 6 is load type. Static loads contribute to creep, while cyclic loads can induce fatigue alongside creep, complicating the failure mechanisms. Number 7 is phase composition. Materials with multiple phases may exhibit different creep behaviors based on the characteristics of each phase, such as ductility and melting temperature. Number 8 is grain boundary sliding. One of the primary mechanisms for creep, the movement of grains relative to one another under stress, can facilitate creep deformation. And here are the critical factors of stress rupture associated with each mechanism. Number 1 is temperature. Similar to creep, high temperatures increase susceptibility to stress rupture. Materials can fail rapidly under stress when combined with high temperatures. Number 2 is applied stress. The level of stress is critical. The relationship between stress and rupture time is often described by stress rupture curves, indicating that higher stress levels lead to shorter rupture times. Number 3 is material quality. Defect density, inclusions, and overall microstructural integrity impact how materials can withstand stress rupture. Higher quality materials tend to have longer rupture lives. Number 4 is time to failure. The stress rupture process is inherently time-dependent. Longer exposure to load and temperature increases the likelihood of rapid failure. Number 5 is stress concentration. The presence of notches, geometric discontinuities, or flaws can create stress concentrations that dramatically reduce the lifespan of a material under load. Number 6 is thermal history. Previous heat treatments or cycles can affect a material's susceptibility to stress rupture by altering its microstructure. Number 7 is environmental factors. Similar to creep, exposure to corrosive environments can accelerate rupture processes by promoting cracking or embrittlement. Number 8 is microstructural instabilities. Certain microstructural changes, e.g., phase transformations, can lead to a sudden decline in material properties, increasing susceptibility to rupture. In summary, the critical factors for creep and stress rupture mechanisms include temperature, stress levels, material properties, time, environmental conditions, and microstructural characteristics. Understanding these factors is essential for predicting material performance and enhancing the design and operation of components subjected to prolonged high-temperature conditions. Creep and stress rupture damage mechanisms affected units or equipment based on API 571. Creep damage is found in high-temperature equipment operating above the creep range. Heater tubes in fired heaters are especially susceptible, as well as tube supports, hangers, and other furnace internals. And then, piping and equipment, such as hot wall catalytic reforming reactors and furnace tubes, hydrogen reforming furnace tubes, hot wall FCC reactors, FCC main fractionator and regenerator internals all operate in or near the creep range. And then, low creep ductility failures have occurred in weld heat-affected zones, HAZ, at nozzles and other high-stress areas on catalytic reformer reactors. Cracking has also been found at long seam welds in some high-temperature piping and in reactors on catalytic reformers. And the last but not least, welds joining dissimilar materials, ferritic to austenitic welds, may suffer creep-related damage at high temperatures due to differential thermal expansion stresses. Creep and stress rupture are damage mechanisms that primarily affect materials subjected to high temperatures and sustained loads over time. They are particularly important in high-temperature applications, such as power generation, petrochemical processing, and aerospace industries. The affected units or equipment typically include: Number 1 is pressure vessels. Vessels operating under high temperature and pressure conditions, such as those found in refineries and chemical plants. Number 2 is piping systems. Pipes that transport high-temperature fluids, often made from alloy steels or other high-temperature materials. Number 3 is boilers. Components that operate at high temperatures and pressures, particularly superheaters and reheaters. Number 4 is turbines. Gas and steam turbines that experience high thermal and mechanical stresses during operation. Number 5 is heat exchangers. Units that transfer heat between fluids at elevated temperatures and can be prone to creep damage, especially in their tubes. Number 6 is reactors. Equipment where high-temperature chemical reactions occur, often leading to prolonged stress on materials. Number 7 is tanks and storage vessels. High-temperature storage, especially those containing molten salts, chemicals, or other materials that may contribute to long-term stress. Number 8 is support structures, components that bear loads for other structures or systems that may be subject to thermal cycling. Number 9 is industrial furnaces. Equipment involved in high-temperature heat treatment processes where materials are subjected to prolonged high temperatures. Number 10 is wind turbine components. Certain components may experience creep under sustained loads at elevated temperatures due to material degradation. Understanding where creep and stress rupture can occur helps in the design, material selection, and maintenance strategies to ensure the longevity and reliability of these systems. Regular inspection and monitoring are also crucial to detect early signs of damage and mitigate risks. Appearance or morphology of creep and stress rupture damage mechanisms based on API 571. The first is the initial stages of creep damage can only be identified by scanning electron microscope metallography. Creep voids typically show up at the grain boundaries and in later stages form fissures and then cracks. The second is at temperatures well above the threshold limits, noticeable deformation may be observed. For example, heater tubes may suffer long-term creep damage and exhibit significant bulging before final fracture occurs. The amount of deformation is highly dependent on the material, and the combination of temperature and stress level, see Figure 4, 17 to 4 to 19. The third is in vessels and piping. Creep cracking can occur where high metal temperatures and stress concentrations occur together, such as near major structural discontinuities including pipe T-joints, nozzles, or welds at flaws. Creep cracking, once initiated, can progress rapidly. API 571 Note. Table 4.3 for threshold temperatures for creep could be referred to API 571 Table 4.3. Creep and stress rupture are two important damage mechanisms that occur in materials, particularly metals and polymers, under high temperature and stress conditions. Here's a detailed overview of their appearance or morphology of creep damage. Creep is the time-dependent deformation of a material under constant load or stress at elevated temperatures. The appearance and morphology of creep damage can vary based on the material and conditions, but common features include: Number 1 is necking and strain localization. Creep can cause localized deformation, leading to a necking effect, where a specific region of the material undergoes more deformation than others. Number 2 is creep cavitation. Formation of cavities is a common feature observed in materials undergoing creep. These cavities appear as voids or small holes within the material, often seen under microscopic examination. This is especially prevalent in ductile materials. Number 3 is grain boundary sliding. Often, creep involves the movement of grains relative to one another, particularly at elevated temperatures. The morphology may exhibit intergranular damage, where boundaries between grains become weakened and can lead to the formation of cracks or voids. Number 4 is microstructural changes. Creep can lead to changes in the microstructure of the material. This may include grain coarsening, increased size of crystals, and precipitate formation, affecting the overall mechanical properties. Number 5 is crack formation. As creep progresses, cracks may develop, particularly along grain boundaries or in regions of high stress concentration. The appearance and morphology associated with stress rupture includes: Number 1 is transgranular and intergranular fracture. Stress rupture can lead to two types of fracture morphology. The first is transgranular. Cracks pass through the grains. The second is intergranular. Cracks propagate along the grain boundaries, often indicating weaker bonding at those locations. Number 2 is surface features. The fracture surface of materials that undergo stress rupture typically shows rough, dimpled features indicative of ductile failure. However, if the material is more brittle, the fracture surface may appear smoother or even crystalline. Number 3 is rupture ductility. In many ductile materials, before a complete rupture occurs, plastic deformation may be visible, often characterized by a necking region that exhibits localized elongation prior to failure. Number 4 is oxidation and environmental effects. In some cases, environmental factors can contribute to stress rupture failure. Oxidation may lead to surface degradation, which can facilitate crack initiation and propagation. Number 5 is dimensional changes. Stress rupture may also result in permanent deformation of the material, leading to changes in cross-sectional areas or overall dimensions, with potential signs of sagging or bending in structural components. In summary, both creep and stress rupture mechanisms are critical in assessing the long-term durability of materials in high-temperature applications. The manifestations of these mechanisms can provide insight into the causes of failure and are essential for material selection and design considerations in engineering applications. Creep and stress rupture prevention and mitigation. Creep and stress rupture are important failure modes in materials, particularly under high temperature and high stress conditions. The prevention and mitigation of these types of damage can be approached through several strategies. Now let's see the prevention strategies. The first of prevention strategies is design considerations. Select materials with high creep resistance. Choose materials with low creep rates, such as nickel-based alloys, titanium alloys, or other high-temperature alloys. Optimize component design. Minimize stress concentrations, use rounded corners, and avoid notches or sharp edges. Use finite element analysis, or FEA. Perform FEA to predict stress distributions and identify potential areas of high stress. Design for reduced stress. Use design techniques such as stress relief, annealing, or shot peening to reduce residual stresses. The second of prevention and mitigation strategies is material selections. Choose materials with high strength-to-weight ratios. Select materials that can withstand high stresses without excessive deformation. Consider materials with high thermal conductivity. Materials with high thermal conductivity can help to reduce thermal gradients and associated stresses. Oxidation can accelerate creep and stress rupture damage. Prevention strategies. The third of prevention strategies to be considered is operational strategies. Operate within design limits. Ensure that the component is not exposed to temperatures, stresses, or other conditions that exceed the design limits. Monitor temperature and stress. Regularly monitor temperature and stress levels to detect potential problems early. Implement maintenance schedules. Regular maintenance, such as inspection and replacement of components, can help to prevent creep and stress rupture damage. Avoid thermal cycling. Minimize thermal cycling, as repeated heating and cooling can accelerate creep and stress rupture damage. Control process variables. Control process variables, such as pressure, flow rate, and chemical composition, to minimize stress and temperature fluctuations. Number 2 is mitigation strategies. The first of mitigation strategies to be considered is stress relief procedures. Use heat treatment processes like annealing to relieve residual stresses in components before putting them into service. The second of mitigation strategies to be considered is post-weld heat treatment. If components are welded, utilize post-weld heat treatment to reduce residual stresses and improve material properties. The third of mitigation strategies to be considered is surveillance and monitoring. Use advanced monitoring techniques, such as thermography and strain gauges, to track temperature and stress in real time. The fourth of mitigation strategies to be considered is maintenance and repair. Establish a maintenance schedule that includes reevaluation of material conditions, possible replacement of high-risk components, or reapplication of protective measures. The fifth of mitigation strategies to be considered is stress redistribution techniques. Use methods that allow for stress redistribution in high-stress areas, such as incorporating flexible designs or the use of dampers in dynamic systems. The sixth of mitigation strategies to be considered is training and awareness. Ensure that engineers and maintenance personnel are trained to recognize conditions that promote creep and stress rupture and to understand material limits. In summary, prevention of creep and stress rupture damage primarily focuses on appropriate material selection, careful design to reduce stress concentrations, and managing the operating environment. Mitigation involves monitoring, regular maintenance, and implementing design practices that can provide more resilience to creep and stress rupture over time. Engaging in a holistic approach to materials engineering can significantly enhance the longevity and safety of high-temperature applications. Creep and stress rupture inspection monitoring based on API 571. Since cracking is usually surface-connected, visual examination, MT and PT are effective methods of inspection. The second is external SWUT inspection can be used for non-intrusive inspection for internal cracking and where reinforcing pads prevent nozzle examination. The third is heavy wall reactor internal attachment welds can be inspected using specialized ultrasonic techniques. Creep and stress rupture damage are significant concerns in materials that operate under high temperatures and stresses over prolonged periods. Detecting these damages early is critical to ensure the safety, reliability, and longevity of structures and components like power plants, turbines, and other high-temperature applications. Various inspection and monitoring methods can be employed, including: Number 1 is visual inspection. Routine visual checks can help identify surface cracks, deformities, or changes in surface condition. Early signs of creep damage may include bulging, sagging, or surface irregularities. Number 2 is non-destructive testing, or NDT. The first of NDT is ultrasonic testing, or UT. High-frequency sound waves are transmitted through the material, echoes are analyzed to detect internal flaws. The second of NDT is radiographic testing. X-rays or gamma rays are used to create images of the internal structure, revealing voids, cracks, or other anomalies. The third of NDT is magnetic particle inspection, or MPI. This method is suitable for ferromagnetic materials and can detect surface and slightly subsurface flaws. The fourth of NDT is dye penetrant testing. A liquid dye is applied to the surface, and the presence of cracks is indicated by the dye rising out of the defects. The fifth of NDT is eddy current testing. This method is effective for detecting surface and near-surface defects in conductive materials by observing changes in induced currents. Number 3 is mechanical testing. Testing material samples for properties like tensile strength, ductility, and hardness can provide insight into material degradation due to creep and stress rupture. Thermography can detect temperature variations on the surface of components, which may indicate potential areas of damage or stress concentration. Number 5 is strain gauges. Strain gauges can be installed to continuously monitor strain in critical areas, providing data that can indicate creep deformation over time. Number 6 is acoustic emission monitoring. This technique listens for high-frequency sound emissions from materials under stress. It can help identify the onset of cracks and failure mechanisms. Number 7 is phase transformation monitoring. Advanced materials may undergo phase changes due to prolonged stress at high temperatures. Techniques like X-ray diffraction can be poised to detect such changes. Number 8 is life assessment and predictive modeling. Use of damage models, like time temperature parameters or the Larson-Miller parameter, helps in predicting the remaining life of components under expected operating conditions based on historical creep data and stress analysis. Number 9 is long-term monitoring systems. Implementing integrated sensor systems for real-time monitoring of temperature, pressure, and deformation can help in identifying conditions conducive to creep and rupture development. Number 10 is metal sampling and specific tests. For more advanced cases, small samples from suspect areas may be extracted and tested specifically for creep and stress rupture using standardized methods. Selecting the appropriate inspection and monitoring methods depends on operational conditions, material types, component design, and the specific requirements for safety and reliability. Regular monitoring and early detection are critical for managing the risk of failure due to creep and stress rupture. Thank you.